He got his BS degree in Greece, then go to US for PhD, then go to MIT for postdoc, and I know he also went to Holland, and his specialty is in cold atom, control and the manipulation for quantum information processing. And when I was in South Tech, I saw him design very fancy equipment. So I'm interested in knowing what's the stage of the installation and what is his recent work. So we are very happy that he is willing to share his work with us and maybe talk a little bit about his lab how his lab has been set up. So let's warmly welcome Georgios.
Okay, thank you very much. Sorry for the trouble. So do we still have 45 minutes or when is the end of the presentation?
You can make it an hour. You can make it an hour, that's fine.
Okay, so I will present everything that I have, and then if we are about to finish, you can let me know to accelerate. Okay, so I can start. Can you hear me well now?
Yes.
Okay. Thank you very much for the introduction. Thank you very much for the invitation. My name is Georgios. So today I will be discussing some of our recent work on cold atom gases with a goal to do quantum information. So I will not be discussing directly about quantum information applications, but how our experiments can enable these type of things. So, 1 second. Okay, so already you gave an introduction of what I have done, my short biography. So I have worked mostly in my PhD in the United States with Christodoulidis in photonics. So I have worked in non-diffracting airy beams and also introduced experimentally the so-called PT symmetry in passive structures. And then I switched from photonics to cold atoms, where I have done 2 postdocs, one at MIT in ultra cold atoms where we simulated the Hofstadter Hamiltonian, and then in Amsterdam in the Netherlands, where I built a new experiment with a goal to do quantum information with cold atomic ensembles. And since 2018, I'm in SASTEC in Shenzhen. So our university has been established in 2011. It's a pretty new university in Shenzhen, Guangdong. And our institute was established only in 2017. There are several labs, and one of the main directions of the institute is like quantum computing. For example, there is ion trap, there is atom tweezers, there is quantum optics, there is superconducting qubits, and also several experiments with condensed matter. So what I will be discussing today has 3 parts. First, I will give a short introduction, why cold atoms can be used for quantum information. Then I will be discussing how in Amsterdam in the Netherlands, we created a toolbox for atomic quantum computing in 2 steps. And then I will conclude with the main part of my talk of how we can have quantum interference in a non-Hermitian atomic memory. So before I continue, can you hear me well?
Yes, very well. Thank you.
Okay, I continue. Okay, so we go to the main part. So the simplest thing is why we want photons is because photons determine kind of is a traffic law of the universe, is the fastest particles, and also it can be a very robust carrier of quantum states. And you can have also quite low decoherence in the lab. And also why we want to do cold atoms. Cold atoms is a quite pure and versatile system. And at this
Sorry, are you stuck? Oh, we do not hear. Anyone else here?
Can you hear me now?
Yeah, yes.
Okay, I continue. Okay, so maybe once in a while you can tell me that you are there, so to make sure that every 5-6 slides.
Okay, I will tell you.
Because I cannot hear anything. Okay, and so it's a purely versatile system, and
Sorry, no voice again. Hello? Giant, can you hear? Okay. Georgios, no voice. Hello, Georgios. You stuck?
Hello?
Yeah, okay. Now, okay, it's working.
Okay. So, and in the first part of my talk, it is related more with how ultra-cold atoms, like in the form of BC or degenerate Fermi gases, and the second part of my talk is related with quantum and nonlinear optics at the single photon level. So there are two directions that somebody can use to do cold atoms. One is to try to do quantum information with tweezer arrays. For example, there is a pioneering experiment by the Greiner, Vuletic, and Lukin group at Harvard and MIT, where they have used a 51-atom quantum simulator with atoms interacting through Rydberg interaction being in a tweezer array. And another direction, and we're also trying to follow here in Shenzhen, is trying to do quantum memory in atomic ensembles. And the main ingredient that we are using is electromagnetically induced transparency that we'll be also discussing a little bit later. So how cold is the coldest? So our work is not about breaking records, but is about being able to see the right physics for the right temperature. So the room temperature is 300 Kelvin, and maybe cryogenic can operate at 1 Kelvin, but if you go to laser-cooled atoms, you have to go to 100 microkelvin. This is the meaning that the atoms move very slowly, so the Doppler effect becomes insignificant. And also, when you release the atoms, they do not escape too fast. And if you go other 3 orders of magnitude lower, you can go, for example, to BEC or quantum Fermi gases, where the also, as we see in this website, in this slide, for Bose-Einstein condensation, when we have very high temperature, the particles behave like classical balls, like billiard. But when the temperature decreases, Bose and Einstein predicted that you can have a pure Bose condensate. That means that the interparticle.
Sorry, no voice again. Georgios. Hello? No voice. Hello? Can you try to not to use?
I can hear you.
Oh yeah, now I can hear you.
Maybe after, if I have my full screen for some time, it stops.
Yeah, maybe you can try now full screen. Yeah.
Okay. Maybe whenever you have problem, you can tell me and I will switch on and off and it will come back.
Sure. Okay.
Please. Okay. So now we need also low temperatures, because if you have hot atoms, there is high disorder in the system. Pretty much you can have big atom fluctuations from different locations in your sample, so then you cannot do a kind of nice measurement. This is what cold atoms achieve. They can achieve a quite ordered state, and now you can go there and know your system very well. So Arthur Askin in 2018 got a Nobel Prize for creating the optical tweezers, and they also found application in other fields such as biological systems. But for our purposes, we want to have a multi-dimensional atomic array like the one that they have demonstrated in Paris, or to make a programmable quantum simulator like the one that they have demonstrated in Harvard. So one of the goals of my work in Amsterdam is to create an engineering toolbox to be able to do quantum information with atomic systems like optical tweezer arrays. So there is similar work that is being pursued in Caltech by the group of Manuel Andres, or other groups like in Princeton with ytterbium, and other experiments with rubidium or cesium. So the two tools that we need is to have the right cold sample, to have atomic transitions that you can address and have cooling, and also have the right state preparation. And also you have to have a microscope to be able to address the atoms individually. So this is what I set up to do in Amsterdam. So this is the experiment that I have designed and built in Amsterdam. And our main focus is strontium, that is in the second column of the periodic table. And as you can see, as you can predict, it has 2 electrons in the outer cell, and this gives extra properties. This is all the atoms have been brought to quantum degeneracy. So strontium, as we see the atomic system like this, it has several 4 stable isotopes. Some are fermionic, some are bosonic, and it has 2 transitions that are helping for laser cooling. The blue transition, as you see here at 461, is the one that is used for initial cooling down to millikelvin temperature, and also for imaging. And the 689 transition is used to have microkelvin temperatures, and also, as you will see, for example, the group of Georgios has made a Fermi-degenerate 3-dimensional optical lattice clock with strontium that have achieved very high precision. So this is kind of some of the immediate application of strontium. So this is the lab that I have built. Can you hear me? Can you still hear me? Okay,
yeah.
I continue. So this is the lab that we designed and built, and it starts something like this. You start with a chunk of metal of strontium, you heat it at 600 Celsius, then you create an atomic beam as this one, and then you slow it in a Zeeman slower, and then you can trap it in the system. To summarize how this works, strontium has a so-called magneto-optical trap. One can achieve millikelvin temperature and the other microkelvin temperature. The meaning of this temperature is that if you are in the microkelvin regime, then you can easily remove all your magnetic fields and trap your atoms with dipole traps, put them in optical lattices, and have, for example, the spin being not significant. So this is quite convenient for cold atomic systems. So as I have discussed, we can have Zeeman slowing, and then we can have atoms in the so-called blue mode. This is this blue sphere that you see in the middle that can have up to the 10 to the 6, 10 to the 7, or even 10 to the 8 atoms at a millikelvin temperature. But this is kind of impossible to optically trap it. So then we'll have to go to another step in the so-called red mode that has a 7 kilohertz narrow transition. And the smallest the line width, the smallest the temperature you can reach. And from there, we can hold it with dipole traps, hold the atoms, and then reach temperatures that Doppler is not important. And also we can control them quite nicely in holding them in a dipole trap. This is what we did. We got BEC of strontium, and also we're able to get Fermi-degenerate gases. And this is kind of how it looks, how the BEC looks. You can have lifetimes of 100 nanokelvin particles with around 200,000 particles. You can go even to 1 million with very high purity. This is a free fall to demonstrate the bimodal distribution of BEC. And similar techniques that I will not discuss now, they can let us go to 1 microkelvin Fermi gases. This is enough to be able to go to the next step. Is enough for trapping, is enough for tweezers, is enough for spectroscopy, as I will show in the next slide. So if you see this slide, in the 698 transition is a transition that are used in the best atomic clocks in the world. And they have a millihertz line width. That means that the lifetime of the atoms in the excited state is too long, and now you can make lasers. For example, they have made lasers around to 20 millihertz broad. while the typical laser diode can be 100 kilohertz or megahertz. So this is much, several orders of magnitude lower. The first thing that we set up to do for quantum simulation and quantum information is to observe this 671 nanometer transition that is quite interesting. It is also a millihertz transition like the one for the best atomic clocks, but also it is possible to control it by magnetic fields. So it is possible now to have an ultra-sensitive magnetometer because the transition is very, very narrow. And this is what we try to observe with single photon transitions. So these are the 2 millihertz transitions that I'm discussing. One is used for clocks. The other we envision to work for quantum information and ultra-sensitive magnetometry. We built these cavities. This is work is in Amsterdam, and we can lock the laser down to a few kilohertz. And with this, we have a degenerate Fermi gas, or a Fermi gas that is at 1 microkelvin. And this, what is the next step, how to observe this type of transition to use for the system. So we start with a laser, we lock it to the cavity as I have mentioned, and we have also an iodine cell. This iodine cell is like an atomic encyclopedia. Pretty much you can use it to know the absolute frequency of any transition as long as you can match it with the right pattern in the iodine cell spectrum. And in the corner, on the top right corner, you see the kind of the simple schematic of the experiment. We have one beam of very narrow, of let's say 10 kilohertz laser. We have the trapped atoms, that is the blue dot, as you'll see here. And then we scan the transition of this narrow laser. And as you see, if we are far from the transition, the atoms are not really affected. But when we hit the right transitions, the atoms are kind of getting recoil and they are removed from the trap. And this is a direct indication through one photon transition, through, let's say, one photon process. Can you hear me now?
Yes, we still go with you.
Okay. Okay. So with this, we can find the transition and find the absolute frequency of this transition. This is exactly what we did here. You see the transitions from the ground state to the excited state. We have these frequencies that before they have been only known up to 30 megahertz, but for such a narrow transition, 30 megahertz is too far to be able to use it. So now we have observed a transition that is doubly forbidden. If you see here, going from 9 has to 5 half is forbidden. And also from going to the 1s0 to 3p2 is double forbidden transition. So this is why this doubly forbidden transition is so narrow. And in order to have such a measurement, we had to wait for a very long time, and we have to use a lot of power to pretty much broaden the transition as much as possible. And here you can see that the spectroscopy of this ultra narrow light is shown in blue on the right part of the figure. And on the left side, we have the iodine atomic fingerprint, spectral fingerprint. So pretty much we can know now with high precision the location of this transition. And this was also a similar effort has been done for the clock transition. Now we have done this for the magnetically sensitive transition. And with this, I will go to the next part of my work in Amsterdam, how I built a high resolution microscope for atomic strontium. So as I said before, we have some specific requirements to do quantum computing with tweezers. We have to be able to image individual atoms. We have to be able to resolve closely packed single lattice sites. And we have to have high fidelity in measurement. And this is what we set up to do. As you see here, you have to have, let's say, 1 micrometer, let's say, cube volume of the trapped atoms, and the atoms can be in the separated by maybe 1 or 2 micrometers. So this is what we have to do. And this is not so easy because the atoms are maybe 20 millimeters, almost 2 centimeters away from the outside, because these machines are quite complicated. So you cannot just bring the atoms so close. So I designed this lens with like this kind of classical optics work, and we have measured by taking from ETH nanoholes that are in the order of 200 nanometers. This is like a standard technique in optics. Pretty much, if you want to measure the diffraction limit of an imaging system, you can use something like, let's say, optical green function. You can use nanoholes or particles or nanofibers that are much smaller than the wavelength. In this way, you can measure. So what you see here is light passing through these nanoholes, and we can resolve it nicely. So the same way, we can resolve nicely atoms, as I will show you in the next slide. So I do not know if this video will play. So now we have the lens, and we move it with respect to the nanoholes, and you will see that we can have kind of pretty much from fully defocused, like dominated by spherical aberration, you see kind of bright spots that correspond to the nanoholes. This is the resolution. And now we can have 640 nanometer resolution. Pretty much we can resolve atoms that are separated by such a distance. And maybe if you're from condensed matter physics, this distance seems extremely large, but in fact, in atomic systems, the particles are trapped by optical lattices. So this is kind of almost ideal resolution for this system. And early experiments, maybe 10 years ago, they have spent maybe $100,000 to get this type of lenses. And now we can have, can you hear me now?
Yeah, still, but I have a question. So
Yes.
each spot there is a single atom or a bunch of atoms? Each spot.
This, what you see in this slide, is imaging of the nanohole, the 200 nanometer nanohole. I will show you in the next slide how we image atoms.
Okay, good.
So this is to characterize the objective. So after we characterize the objective, we kind of made some theory based on aberration, and we see that our experiment is quite in agreement with the theory, and we see that we can have maybe 1 or 2 micrometers depth, and also have a Schreck ratio that indicates how much, let's say, good intensity you have within the diffraction circle. And this is kind of the characteristics of this microscope. It has resolution. We can use it to resolve 200 lattices in 1 dimension. And we can use this just by tiny modification to use for several wavelengths. For example, the imaging transition for strontium is 461, but you can use it for 432. You can use it for the 671, that is a transition that I described earlier. And now we go to your question. So this is the work that has been done in Amsterdam. So they can image and trap atoms with this microscope. For example, here you can see they can trap like less than 10 atoms. And the next step is with this microscope, they can trap a 2x2 array of single atoms. And now they have gone to a 4x4 atomic array. So this is kind of, possibly this measurement is an average of many measurements, because it's not so easy to load an atomic array every time with 16 atoms. But this is kind of the measurement. And this is kind of where this field where this lab goes. And now they want to do Rydberg atoms with these tweezer arrays.
So the separation is micrometer?
Yes. So the separation is in the order of a couple of micrometers.
Okay. And each of them has tens of atoms, roughly.
No, it can have even 1 atom. So this was the initial measurement. So they go in the mode, they have extra beam, they can trap less than 10 atoms. But now the progress is that they can have even, on average, maybe half atom.
But this is quite surprising because atom is nanometer size and separated by micrometer. It's quite surprising to me.
Yeah. It is possible because now you have a gas. So you are using a trap. You are using a tweezer trap to load atoms on the individual traps.
I see. Okay.
So it's not in the condensed matter that the separation is in the order of angstroms. So you can have atoms in this, it's just a gas, and you load atoms on the individual traps.
So the interaction is still strong enough for them?
So this is why they want to have Rydberg atoms, so they can bring them close to maybe to 1 micrometer. So then the interactions can be strong.
I see.
What you see here, 4x4, is just the, let's say, having the tweezer. In order to enhance the interactions, you have to bring them close, and Rydberg is one way.
Okay, got it. Thank you. So
this is the team in Amsterdam, Florian Schreck, that was the first to have strontium BSc, and this is the team that I was working with, the PhD students and master. And with this, I want, of course, to thank Marie Curie that supported me during my time in Amsterdam. And with this, I go to the last part of my talk, and this is the experiments that we have been doing here in Shenzhen. How much time do I have? 20, 25 minutes or more?
Yeah, roughly 20 or 30 minutes.
Oh, okay. So now we are going to the last part. So how to do quantum interference in a non-Hermitian atomic memory. I will try to explain all these terms. So this is the team. So I'm working together with Chen. So like 2 people are working in one, let's say, one lab. These are the students. We have postdocs, some graduate students, and some master students. And these are kind of, let's say, the main goals that we want to pursue. We are part of the quantum measurement and quantum precision laboratory, and this is the Cold Atoms Quantum Optics Lab. We want to pursue quantum storage, and this is quite a strong field, quite a hot field, and I think there are several groups in Taiwan that are quite strong and are maybe world leading in this field, and some of them are in cold atomic ensembles. Also, you can do it with ion-doped solids. We have a lab in our institute, NV centers in diamond, and also microcavities. And one of our goals is to do also quantum metrology. So we can do magnetometry, we want to do quantum imaging, or we have some proposal to do atomic interferometry in a non-linear interferometer of cold atomic ensembles. So what we do is we try to do we are doing extreme nonlinear optics with atoms. When you have atoms in a cold atomic ensembles, the interactions can increase and we can have a collective state. And then because of the very narrow transitions of atoms compared with the room temperature solid, we can increase the quadratic nonlinearity or the cubic nonlinearity by several orders of magnitude. And for this reason, we can do nonlinear optics at the single photon level with low power and very high spectral purity. This is maybe a big advantage of cold atoms. So this is the experimental toolbox that we have already in our lab. We can laser cool atoms down to 100 microkelvin. You see them in this slide expanding. We can do electromagnetically induced transparency that is related with storing photons in an atomic system, as you will see here, and we can do slow light, and also we can generate entangled photons, all this in an atomic system. And we are using this with one of our goals to do quantum memory. So this is what I have said. One of our goals is to be able to store photonic qubits in more than 100 microseconds, and also to do distance entanglement and through quantum storage. You see here 2 of the works. One of them, I think, is led by a group in Taiwan, where they have the record efficiency of 92%. And the meaning of this is that you store light in a coherent pulse and you are able to retrieve 92% of it. So we want to be kind of in that range and exceed the storage time. And also we want to store qubits and be world competitive in the efficiencies, fidelities, and the duration of storage by applying several tricks. So now I'm going to the last part of my talk to go to the, so as I said, storage is one of our goals. What we would like to demonstrate is that photons that are stored in a medium and they are retrieved can be kind of identical with the atoms that are stored in the medium. So in order to do this, you have to do like quantum interference in an atomic memory. And we do this in a non-Hermitian system, and I will explain what versatility this gives us. So I guess all of you know, or at least heard, the Hong-Mandel experiment. So this is pretty much a fundamental experiment to be able to show that two bosons can be indistinguishable. So when Hong-Mandel did this experiment, they started with two entangled photons. They put them in the beam splitter and they measure what is the chance to coincide. And what they have observed, that photons want to bond together. And this is kind of a proof of their quantum statistics and also kind of a proof of their indistinguishability. Initially, they proposed this as also a way to do precision measurements because overlapping two photons requires very high precision in controlling the system. So if you have a linear beam splitter, maybe you are familiar with this, the possibilities is at the two photons, they will go to opposite detectors because they are reflected or because they are transmitted, or they can go together to the same detector. If they go in the same detector, as you'll see here, then the coincidence detection will show 0. Pretty much there is no detection if we go in this case. And especially if we go a lossless, symmetric 50-50 beam splitter, then we can demonstrate that the only possible state is the one that corresponds to bunching of photons. The photons want to go together like a pair, or they want to go to the other detector as a pair. This is the terminology is like bunching coalescence. And this is kind of a schematic. As you see, the input photons are coming from the left, and because they are indistinguishable and they obey bosonic statistics, they want to come in the output in this unnormalized state as 0, 2, or 2, 0. And this is kind of maybe the best way to prove that two particles are indistinguishable, two bosons. But when we have fermions, the things are exactly the opposite. Fermions, as we know from the Police principle, they do not want to be in the same spatial mode. So this is what happens in a beam splitter. The photons or the fermions will collide and will end up in the opposite detector. And what you will see an excess of coincidence as it is shown in this figure. And can you hear me?
Yes, still.
Okay, I continue. Okay, so to summarize this, it is possible to go to a beam splitter. You go with two pulses or with two particles, 1 and 2, and you can detect in the output if the two particle coincidence. If they are bosons, they will tend to bunch and go to the same detector. But if they are fermions, they want to be unsocial and avoid each other and go on the left and right detectors. So this is the kind of the smoking gun, the signature of their statistics. So this experiment is kind of textbook experiment, has been done in many different systems, has been done for bosonic atoms by the group of Aspect and Westbrook in France, has been done, I think, in Japan for phonons, like you can do it for collective excitations in trapped ions, and by the group of Jianwei Pan, they have done the Hong-Mandel in collective excitations in an atomic ensemble. So pretty much they have two spin waves and they make them interact and they see that they can coalesce. And this, if we go to condensed matter physics, this is also possible with electrons. The group of Yamamoto and groups recently, they have demonstrated very clearly that you can have quantum interference between electrons in a beam splitter, and they have done it in quantum dots and other systems, as we'll see here. So to show this again, photons, bosons have zero coincidence, very low coincidence. Fermions, they have high coincidence. But now we go to a system of plasmons. As you may know, plasmons are bosonic excitations, but now the group from France has demonstrated that in one plasmonic system, you can have bosonic correlations and fermionic type correlation. And this is quite surprising, and you can ask ourselves why this is possible. So this is kind of what we'll discuss today in atomic systems. So in 2021, there are two experiments with lossy metasurfaces with photons that have demonstrated similar things, where you can have photons that are the archetypical bosonic particle that can behave as fermions and as bosons. And this can be explained within the field of non-Hermitian interaction. If you see in the green square, when we have a beam splitter, there is a phase that can control if the system is Hermitian or non-Hermitian, or if it is unitary or non-unitary. This, for example, the lossless beam splitter has this phase phi to be pi over 2. But if you go to other phases, you can have a system that can be lossy or it can be non-unitary, and this can open the opportunities for very versatile physics, as I will show you in the next slide. So this is related to the non-Hermitian physics that my PhD advisor pioneered towards the realization in experimental systems. So when you control the hermiticity, meaning if you control the gain and the loss in a system, it is possible to go to physics, for example, to have exceptional points and to go to systems where the eigenvalues can become complex, go from complex to real. And so this is kind of a general, very hot field. So now what we are doing is we want to modify quantum interference, that is a fundamental process, via hermiticity, and you have this as an application in quantum memory. Because if we prove that the photons and the atomic coherence are indistinguishable, we have kind of a strong indication, a strong proof that these two particles can achieve very high fidelity. So it is possible to have bosonic interactions in a unitary system. When you go to a non-unitary, you can have fermionic interactions, and you can even have anions. That is kind of like fractional statistics. So we have a degree of freedom that can control going from bosons to fermions. And this is what we have demonstrated. So as you see on the top, if we have a beam splitter that is kind of a fundamental element in any quantum network, and usually you have a 50-50 beam splitting ratio. But if the system starts having losses, you go from, let's say, 50% to 25%. Now you can open a whole sea of phases that you can control the quantum statistics of particles. This is a figure from the 2021 paper, and also something similar has been demonstrated by 2019, as I will show you by Chen, this is my collaborator. So I want to mention that this modification of quantum interference is totally different from two other cases that I'm discussing here. If you are familiar with the Tomsky-Ardot ultra-cold gas, it is possible by increasing the interaction between bosons to make them behave like fermions. Pretty much, they will never want to go to each other because the repulsion is extremely strong. Also, in a unitary system, lossless system, by polarization control, they have demonstrated that it's possible to access different type of statistics, even with photons. But what we do here is storing photons in atoms. As I said, this is the EIT system. So this was kind of pioneered by Flashauer and Lukin, where they demonstrate that is in a controllable way, you can store light in atomic coherence, and you can retrieve it at will. This can be described in a spin wave. So this pretty much is high excitation, many excitation system where you have the different coherences at different locations and they have a different phase. So this is kind of a spin wave. If you go to the elementary excitation of a spin wave, this is the magnon. That is what we are doing today. So this is the system that we have. We have a beam splitter that we can do it in an atomic system now, where the two inputs, one is photons and the other is spin wave or atomic excitation. And as you see in the blue light here, we can have delta to control the strength of interaction or to control the statistics. So this is exactly what we'll do. I will go a little bit faster. I assume that I have like 15 minutes, something like this.
Yes, you can go.
Okay. Okay. So in order to have this magnon photon beam splitter, we have to be able to control light. And this is done with like a EIT system. We have the blue arrow here, that is like the probe, is the input light. And with a coupling beam, a control beam, we can control how much of this light will be transmitted in the beam splitter and how much of it will be stored in atomic coherence. And the spin wave is like a superposition between these two states. It's like a superposition of coherences, as you'll see here, and we can control it in the same simple system. And now, if you put this spin wave and light, we can start seeing interference. When the excitations are very high, like when you have input of two coherent states, the system can be described like this. For the coherent pulse or for the single photon, you can have light and spin wave in this rubidium system. And you will have all the degrees of freedom to control the transmission and the type of interaction. This, if you go to the limit of optically thin medium, you can transfer from equations of motion to like a beam splitter type of system, as you will see here. And now I will go to kind of schematic. We have light in this atomic system can be converted to light or magnons that we can put two independently in the system can be converted to light and magnons. As you will see, this is a generalized beam splitter matrix that we can control the transmission, reflection, and also the phase. And this phase, θ1 plus θ2, determines the way that the statistics will happen between particles. So they have demonstrated this from the initial experiment with classical interference. So we can see that it's possible to go between spin waves that go together with light, or light and coherence that they go opposite. But so what we said, yes?
I'm confused. The law of spin wave and the light, are they playing the same role, or the spin wave is the main target and light is going to probe it? I'm not.
Okay, so. Next slide will answer. Let me go to show this thing quickly, to show the setup. So what we have here, we have a two-dimensional mode, as you'll see here. So light will go from the left side to the right side of this mode, of this white line. And we will be able to control by the coupling beam if the light will be absorbed or if it will be transmitted. So one part is light. The other part of the experiment is independently, we create also atomic excitation in the system. So we create atomic excitation, we create light excitation, we let the quantum interfere in the medium, and then we detect them out. So we have both independently. Because, for example, if you want to store particles, you can store it, and then you can assign the next system, for example, to retrieve it or to control the output. So maybe I will go here to, so what we see here, we shine light in the system, and at the same time, we can create also a spin wave. And if you see here, if we scan a phase, the relative phase between the pulse of light and the pulse of spin wave, we can see that in one case, they can go together, like if they are fermions, and on the other side, they can be completely opposite if they are bosons. And also you can have access to anything that, for example, you can go to pi/2, it looks like anions. But this is totally first order interference, classical interference of a spin wave with a light wave. But what we are after is to do quantum interference between single particles of atomic coherence and light. So this is a summary of what we want to do. And this is the experiment. Yes?
Some excitation of the atom collection by the light. So does this has to have the magnetic property from the beginning so that they can have spin wave excited?
Okay, so these particles is, for example, when you have ground state atoms, you can apply the right to a Raman pair of beams, and you can excite some of the particles in an excited state. So you have two states, so they can create the superposition. And by these two, a Raman process can create a superposition between ground state and excited state. And if you go to the magnon, what we call magnon, this is maybe in quotes, is a single, maybe I can go to the specific formula, maybe it's more helpful. 1 second. Here, to answer your question. So what is the magnon? Is you have all the atoms being in the ground state besides one that is excited. So, and whenever you have all this superposition of possible states, all the atoms in the ground state besides one, but we do not know which one, this is a single excitation or a single atomic coherence. This is kind of what we mean by magnon. Is it clear?
Oh, okay, thank you.
Okay, so now I will go to the setup. So what we set up to do is we have the magnons, that is a single, only one atom excited. Then we shine light, and then we can let them interfere in our system, and then we detect with a single photon counting modules the output. We can detect the photons, and we can detect the magnons, and demonstrate that they are kind of identical. They can be identical, even though that they are two completely different stories. One is purely light, the other is atomic coherence that is kind of retrieved. And this is kind of the lab in Nansan in our university. You have the atoms and you have the laser table, and this is how it works. First, you go through with the EIT system. You shine light, and some of this light is converted to atomic coherence. Some of the light is transmitted, as you have asked me. So the transmitted light is one port, the stored atoms is the other port. And we can do the same, and this is how we do it. We can measure the photons, we can measure the magnons, and we can do the same with the magnon input. So now, I'll go a little bit quickly. We have this interference. We have magnon states, we have photon states, and we do a Hong-Mandel experiment. And it looks like this. So each time we do 3 experiments. Only photon input, only magnon input, and we use this to characterize the off resonance coincidence, and then we do the quantum interference. And we have to show what you see here. Quantum interference is the coincidence between photon and magnon when both of them enter the system. And we have to compare it with a photon and magnon accidental coincidence, as you will see here. And this is, we do this, we have to characterize our sources. So our magnons, we make them through a DLCZ process, that is a kind of a framework to create single particles. So this is what we do. We characterize the self-correlation of this system. And when it is below 0.5, it is even better than the two photon Fock state. So we are around 0.1, 0.2. And we have light that is highly attenuated light coming from a laser. This is why you have a G2 of 1. So when we use this in the system, we have developed a simple theory that you can predict exactly what the quantum interference will be. When you have control of the phase, you have control of all the transmission, and you have two systems. When you have ideal system, everything will be like a dust line. When you have almost ideal but not perfect single magnon, you can have theories like this. And this is our first experiment. If you see on the top left, when we choose the phase to be like bosonic, and we have a suppression of coincidence as you see here. This is similar with what the classical Hong-Mandel experiment does, but now we do it for the first time between photons and single particles of atomic coherence. And this is kind of boson bouncing. This is, now it is possible to control, to switch the phase and have completely the opposite process, to have fermionic anticoalescence. So pretty much to have an excess of coincidence, as you will see here. And when we do this measurement, we can control the photon number. As you see, the average photon number in the 1R is maybe 0.02 photons per experiment. And with the green, you can see the classical everything that is within the classical limit, whenever you just take two laser beams and you interfere them. But if you go to lower than 0.5, you go to the quantum regime, as you'll see here, and we exceed it by a few standard deviations. And if you see the blue dot corresponds to the inset, as you see here. So we have a quite strong and very clear photon bouncing. But this is not the only thing that we can do. So if you have Fock states, you can go perfectly to 0, but you see our system is not perfect, but still very clearly within the quantum, exceeding the classical limit. While if you have completely coherent state input in your system, you can never go lower than 0.5. So this is kind of a purely quantum manifestation. And if we go now to the other case, that we control our system by choosing to go on resonance, we have fermionic antibouncing. So now everything that is above 1.5, the correlation function, is in the quantum limit. And you see for the red dot, we can exceed this for a couple of standard deviations as we vary the photon number. This is kind of, as you see, the theory and the experiment are matching rather well. So we have a good control. So now we can go to any type of statistics, but with this type of system, and we can predict exactly how it will happen. So the visibility is kind of in the order of 0.7. And we can have very corresponding things for the Fock state for fermions. Fermions predict that we can have a very big range that we are exceeding the 1.5 number, and we can have anti-bouncing. So now we have demonstrated the same way that Hong-Mandel demonstrated this for photons. We demonstrate that for photons and single magnons, we can have quantum interference that can also switch from bosonic that shows indistinguishability to fermionic that shows excess of coincidence. The same way that you can have coherent state that can let you go only above to 1.5, but when you exceed the classical limits, you can go to higher values as we go in this experiment. So we demonstrated fermionic enhanced coincidence and bosonic suppressed coincidence, similar with the Mandel, but in a hybrid system between atoms and photons. And this is kind of the ideal predictions. And one last part, maybe 3 minutes. So what I demonstrated before, that in optics is not possible to, in pure optical system, you cannot store light for more than a few nanoseconds if you don't use cavities. What we can do here, and it's very different, and this kind of has one application towards quantum information, is that we can store the atomic coherence and we can prove that the indistinguishability can have a lifetime. So we have optimized our system to make sure that we are not limited by coherent pulse lifetimes. Our experiment lasts only maybe 3 microseconds, while our lifetime of storage is maybe 20 microseconds. And now we want to show that we can store the magnons and then perform quantum interference, or we can perform quantum interference and then store the magnons, and then measure how long the magnons start. And this way shows pretty much that our system can have quantum interference in extended times, a few microseconds. So this is the sources. We have characterized our sources that they stay below single photon level and they stay coherent for this period of the experiment. And then these 2 slides, one is that we saw that for bosons, we can store this, let's call it indistinguishability, from 0 to 5 microseconds, and afterwards noise is limiting our system, so kind of we can have a few microseconds of storage, and this is kind of pretty much impossible in plasmonic or photonic systems. We demonstrate this also with fermions. We can have maybe 2.5, 3 microseconds of storage, and this is not. This is maybe an order of magnitude lower than the lifetime of our system. So possibly this decay of quantum interference can happen because of some small increase of the magnon quality. And with this, I'm going to the last 2 slides. So 2 possible applications, some applications that we are envisioning about this system is that not us, but other people can take it in non-Hermitian other systems like ions or diamond memories. So there is an earlier experiment from 2015 that they have demonstrated in a lossless beam splitter or a Hermitian beam splitter an interference between single photons and atomic coherence in diamond. Another thing that we are thinking is we can do quantum simulation of anionic interactions. For example, there is a paper by Farah and Cooper where they can show that you can have in a magnetic potential, when you are in the lowest Landau level, you can have anionic signature, and something can be very similar to a beam splitter of anions. So now we can demonstrate a beam splitter of anions even at the single particle level. So this is one possible application, possible direction. And another idea that we have not make it very solid, but this is kind of a vision. So boson sampling is nowadays very hot because you can prove kind of computational primacy or supremacy, and boson sampling is a very hard problem. But fermion sampling is considered a mock-up and easier system. But if we can manage to have several of these beam splitter in one atomic system, and this is kind of by sequence of pulses and kind of some retrieval of signals, maybe we can try to do fermion or even boson or even anion sampling in a simple system like this, if we manage to perfect our beam splitters and put them together. And with this, I want to acknowledge Professor Chen Fei, the students, and Professor Zhou from USTC that helped us with the theory and also the funding agencies. And with this, I go to the last slide of my talk. So we have now we have one experiment in the campus and two more experiments in the Quantum Institute. So now we have already two working machine, fully working machine that I have reported this work, and we have two more experiments that now we have laser cooled atoms, and we have several ideas from like biphoton structured light to artificial intelligence at the physical layer with using EIT, and also one idea that we are also trying to fund is to have a system of atoms to act as a complex physics simulator. Pretty much with the EIT, you can control locally the potential, and you can study Anderson localization, you can study biphoton propagation, you can study entropy, entanglement, unscrambling, and things like that. And with this, I want to apologize for the technical difficulties at the beginning, and thank you very much for your invitation. Be free to answer any questions you have. Thank you.
Okay, thank you.
Maybe I can go towards, leave the full screen and go to the chat.
Okay, thank you for the very nice talk. And any question or comment from the audience? We have a tense audience in the meeting room, and also 4 to 5 person in the online.
Okay, nice, thank you.
Thank you.
Please take advantage of the questions, because we were maybe rushed a little bit because of these technical difficulties. So you can ask me and we can go back anywhere you want to the slides.
Okay, may I ask the source of the non-Hermitian?
Yes.
Because it looks to me the boson, it looks like you showing one PowerPoint, one slide that fermion has more non-Hermitianity, and then boson, because non-Hermitianity leads to loss, right? So
Yes.
is that the Pauli exclusion principle leads to this kind of loss in the non-Hermitianity?
Okay. So I will go to this slide. So the system. So let me be very clear again about this boson and fermion. So what we can change is the interface that couples photons to atomic coherence, and we make it such that two single particles, let's say, like one single photon and one single atomic coherence, they can behave, they can have coincidence statistics similar to bosons, similar to fermions, even though that in their nature they are photons, and atomic coherence that is a photonic, it's a bosonic excitation. So the loss in the system comes here. So there are three terms in this Hamiltonian. The first term is it counts the number of photons in the system. The second term counts the number of excitations in atomic excitations. And the bottom in the light blue is the beam splitter interaction. If you see here, there is the delta I gamma 1,3. Gamma 1,3, we cannot change it because it is related with spontaneous emission in the system. It's kind of, if you choose the atom, you have the gamma 1,3. But what we can change is the detuning, the single photon detuning of the laser pulse and the coupling beam. And now this creates a complex phase in front of the atomic beam splitter. This complex phase can create the non-unitary system, and also for the non-Hermitian that is associated with loss. There are two paths to have loss. One path is, as you see here, through spontaneous emission. So the photon can be lost and not end up in the same spatial mode. So it can end up in other directions. So pretty much we lose the photons. And also the atomic coherence has another path to be lost. And this is through the ground state interaction between the particles 1 and particles 2. For example, these particles are moving. They can start interacting because they can collide, they are hot, and then you can pretty much start avoiding the coherence of the system. And also we can have, besides loss, we have also decoherence in the system, but we try to minimize this. So this is how we can modify the phase. And for example, you see this in this slide, delta, and you see here, we can control these phases, theta 1, theta 2, that they are related with the unitarity of the matrix. And this is kind of how, and this is the physical way to control all the terms in the system. You can change the optical depth, you can change the detuning, you can change the power of the coupling, and you can change also the pulse of the pulse width of your probe beam, of your photons.
Okay, so the level 1 and 2, 3, all these are determined already be in the system excitation and control all these detuning, something like that.
Yeah, we're controlling the detuning, the power, the pulse width. Yes.
Okay. Yeah, this Professor Chen has question.
Yes.
I'm Chen from National Science University, and I'm a question about this whole momentum interference.
Yes.
In this slide, I think you use a pole laser and a coupling laser to generate a stall photon and anti-stall photon. And
Yes.
in your previous slides, you only use a slow light to mention. Slow light is a superposition of the electromagnetic field and the spin wave. I'm curious, which system do you use to demonstrate the whole momentum interference? Is it a forward missing transition or a quantum memory transition?
So, okay. So the system that we use to do this is an EIT transition. So we have an EIT. So, okay, maybe I can just go 1 second. Maybe I'll just go to where I saw the physical system. So here, okay. So this is the physical system. On the left side, where you have the blue and dark blue and light blue, we have the DLCZ to be able to create the single atomic excitation. And on the right side, we have a standard EIT system to be able to store photons. So the four-wave mixing is not used to memory. Only the EIT is used for quantum memory. The left part that in principle could be, we are using in other experiments for four-wave mixing, is only used independently to create with DLCZ the single magnon, the magnon.
So now I understand. So you use a forward missing transition to generate a single photon, and the generated single photon is the Pole field, and you make the Pole field become a slow light, and you use the superposition of the slow lights, which includes the electromagnetic field and the spin wave, and the spin wave is the magnet you mentioned in your talk.
Okay.
So you may show the whole momentum interference for the spin wave. Is this correct?
Let me clarify it. So for the spin wave, we create single excitation through the pump. We shine the pump beam, and we are able, when we detect one photon, to know that we have one magnon stored in the system. So for the spin wave, in fact, we have magnon. We have only a single excitation. But for the light, we don't use four-wave mixing to generate the photons, but we use a highly attenuated coherent light in the level of maybe 0.1. So the Hong-Umander is between a single particle of atomic coherence with Z2 close to 0, and extremely attenuated coherent pulse in the order of 0.01 photons per pulse. So the photons are not generated by, can you hear me?
Yes.
The photons in this experiment are not generated by four-way mixing, but the perfect experiment is to have single photons from four-way mixing and magnons from the DLCC. This is the perfect experiment, what you described.
Okay. I think this scheme is called the spontaneous four-way mixing transition, and this is the best way to generate a single photon source.
Yes, yes. So this, in fact, in our new experiment, we have two modes. This is our goal: one to have biphoton source, and the other to use the single photons. But in this experiment I'm reporting here, we had only one mode, so we did not have a simple way to have single photons and single magnons. So we have highly attenuated laser light interfering, quantum interfering with single magnon. I'm aware of what you are discussing.
Okay. Another question is about the interference. The spin wave frequency, I think, is around few gigahertz, and for field, the frequency is around 300 terahertz. How can these two fields have interference?
Okay. So the interference, okay, let me explain. So you have a photon and atomic coherence. The atomic coherence is stored like in the spin wave, in the system. The photon enters the atomic system and then they interfere through the conversion between spin waves and electric field, like in my slide here. So this is kind of their interference. And then we can collect them output as photon modes. So light is transmitted and we can collect it directly and then wait some time because the system has storage and shine the coupling beam, the 1-3 transition, the 2-3 transition to retrieve afterwards the magnon, and we measure it through light. So these two things are interfering inside the medium, and we measure them. The detection is through, let's say, the anti-Stokes photons. So pretty much, let's say, you are bridging the gap between the 3 gigahertz and the 780 that corresponds to hundreds of terahertz by a 2-photon process that is maybe spontaneously coupled, the coupling and the probe. This is what matches the energy, let's say.
Okay. And the beam splitter in this system is controlled by the coupling field, the Rabi frequency of the coupling field, right?
Is controlled by several things. For example, the phase of the beam splitter to go, let's say, from bosons to fermion-like statistics. This is mostly controlled by the detuning, the single photon detuning delta. And then the strength of the transmission and reflection of the photons and magnons is controlled, as you said, by the coupling beam and also by the pulse shape. Because, as you know, if you just go to EIT, the photons will pass. You don't have any control of the transmission, but you have some control. But if our system is like a transient, pretty much you have a pulse, and some part of the probe beam doesn't belong in the EIT window. So for this reason, we have extra loss.
Yeah. Okay, thank you.
Okay, any further question or comment? Okay. If not, let's thank Dr. Siviloglou again. He gave us a very nice talk today, and thank you all the question.
I thank you very much.
Okay, thank you very much. Okay, thank you.